So we are all on stage, and we now can start having the questions to the screen. This question is addressed to Infineon. What are the benefits of the latest Infineon CoolSiC MOSFET products, and how can they help the system designer?
So, as Infineon representative here, Andrea Piccioni speaking from Villach site, and maybe it was referring to the new low ohmic launch of our discrete device in TO247 package. And there are new features on that. First of all, it will be the first TO247 with .xt technology, so the diffusion soldering. This will enable us to have huge benefit in RTH and ZTH. So basically the conductivity widely increased, bringing a lot of benefit from output current perspective or reliability, or also both. I mean, you can combine both benefit and making the right trade-off. Secondly, we enhanced our gate voltage window. So basically we have an enlarged voltage window enabling the transient voltage up to -10 volt. And this will bring us easy and feasibility of the gate voltage design.
Thank you, Andrea.
Welcome.
The question is addressed to Lem. What is a hybrid transducer?
Okay, so I'll take this over since I'm representing Lem today. A hybrid transducer is what we call a transducer that is made of an ASIC, which will be, let's say, sensing low current sides and low frequency, and then a pickup coil, which will be sensing all the high frequency side of the signal. So this is what make possible for our HOB product to sense up to 1 megahertz. And it's hybrid because it's a fusion of ASIC technology and a pickup coil. So again, ASIC is going to consider and pick all the low frequency signals, and then the pickup coil using, let's say, current transformer capabilities will be used for high frequencies of this signal.
Thank you.
Yeah, you're welcome.
So we are able to go to the next. The question is addressed to Microchip, to Rob.
Yes.
What were some of the challenges in developing an SiC-based power stack when compared to an IGBT version?
Mm-hmm. Yep. Thank you, Bodo. Thank you for that question. And we developed a power stack evaluation system, a silicon carbide power stack evaluation system, along with Mersen. And Mersen brought the expertise of bus bars, cooling, and capacitors to the table. Microchip brought the power semiconductors and the gate drivers to the table. And we got to experience by doing that what our customers do. As well. And of course, what a lot of customers do is they start with their IGBT power stack. This is a 3-phase 150 kilowatt inverter. And then try and drop in their IGBTs and similar capacitors, bus bars otherwise, and feel that they're just ready to go. And what they learn is a lot of challenges emerge. One is with regard to heat dissipation. So whereas you would think that silicon carbide, I guess some might think, would run cooler. Because the goal is to operate them faster, they end up switching faster and end up operating, in many cases, hotter than an IGBT and also very centralized. So your cooling becomes a very unique challenge. Your capacitors also now need to also deal with the ripple currents that emerge from the high switching frequencies. You have to keep a real tight eye on EMI as you move into the higher switching frequencies as well. And that's where having our digital configurable gate driver enabled us to modify the turn on, turn off switching profiles of the device through software rather than having to go back in and change through hardware. And we had to go through a whole series of iterations on changing the profile of the turn on and turn off voltages to tune into the optimal settings. So I won't say that when you move from an IGBT-based power stack to silicon carbide that nothing translates. I mean, the components are still there: capacitors, bus bars, cooling systems, your power semiconductors, your gate drivers, your current sensors, and we did use some nice current sensors from LEM in that package as well. All of the basic components are there, but when you then try and integrate them in a silicon carbide system, the dynamics all change fairly dramatically. So having flexibility in your gate driving circuitry, for example, makes a big difference.
Thank you, Rob.
Are
Next
these?
question is, are these available for purchase and where?
Yes, so we have recently announced the availability of these evaluation systems, and they are in fact available for purchase, and they'll be available through distributors. Initially, Richardson, RFPD, will be offering these, and there may be other distributors in the future, but today they are available, and they're available through Richardson.
That sounds good. I like to hear Richardson RFPD. There is a gentleman who his last name is Rostdeutsche.
Yes.
That's very German.
Dave will be at PCIM, so perhaps we can all share a beer together.
We will be first time out to a show. Holger and I go to PCIM. We will have the booth. So looking forward seeing you or all who make it to PCIM.
I look forward to seeing you, Bodo.
Long time ago that I sneaked in Philadelphia and made a surprise to you. Okay, we can have the next question. So to Infineon, what's the major difference, improvement between the first and the second generation of SiC technology from Infineon in terms of device design?
Well, we are not speaking about if it's referring to the question before and the answer of before. We are still calling one M1H generation, so it's for discrete device at least is labeled like this, so it's still the first generation. What is the difference, and I have spoken before, is related to the new low ohmic launch. So means the 7 million, 14 million, 20 million, and the new 40 million. That means nothing related to generation-wise, but related to the million range. Then we just improving generally our front-end, back-end technology. With that, we can come to the point I have above mentioned, so the enlargement of the gate voltage window from the gate side. Moreover,
thank you, Andrea.
The .xt, so thermal performance-wise, so the diffusion soldering, enabling the next level of output current.
That's a question to Qorvo.
Hi,
what
thanks.
are the advantage of the SiC JFET when it comes to short circuit performance?
Yeah, so the vertical JFET is really low RDS on specific device. So it allows die shrink. So this usually comes at the cost of short circuit performance, because short circuit is essentially at the time scales that silicon carbide is able to achieve is more or less adiabatic. So the heat stays in the active layer itself. But because the transconductance of the device is very high, you can tune the saturation current with very minimal compromise in what's your nominal on-state RDS on. So you can tune the device for short circuit performance without giving up too much in specific on resistance. You know, there's additional benefits because, you know, it's a bulk transport device as well. And so you don't run into any kind of hot carrier or trapping effects when the junction temperature rises by high temperature stirring.
Thank you. It's to Microchip, to Rob. In your article, you speak about 700 to 1200 and 1700 and beyond. In which voltage classes is the stack offered or planned?
Yep. Thank you, Bodo. I'm having a little hard time getting my screen here to work, but can you hear me okay?
Yeah, we hear you.
Okay, great. So yeah, so today we offer the stack with 1200 volt devices. In fact, we use the traditional 62 millimeter package that's very commonly available from Microchip and other companies in the industry. So 1200 volt and current rating of about 350 amps per phase. So that's our current offering, but we are also working with Mersen on other evaluation systems up to 1.7 kV, and also looking to include our new SP6Li modules, our very low inductance modules. Now, I think, as you know, Microchip did introduce a family of 3.3 kV SiC MOSFET devices and diodes within the last month or so. So we are also taking a look at that, but that'll likely require a much different design than what we have for the 1.2 and the 1.7 kV devices. But we also, as we come out with new voltage classes, and we offer, you know, as you know, a very wide range of voltage classes, that we are looking to develop evaluation systems at each of those nodes.
Thank you, Rob. Looking forward to the next question. The question to Lem: what is Hob D IDT and response time performances compared to a classic open loop sensor?
Yep. So thank you, Bodo. This question, yeah, could have been easier to answer with a plot, but basically, classic open loop sensors, they have response times anywhere between 1 microsecond and 4 microseconds, depending on the technology used. So, and usually when we use this with classic power switches, it's not a problem. Now we know with the trend with SiC, we need to be much quicker, and we also need to protect much quicker. And this is why with the Hob product, the response time is improved by a factor of 10 almost. So we are having a response time of 100 nanoseconds or 150 nanoseconds typically. Maximum on 100% of the parts, it will be 200 nanoseconds. So it's really a huge improvement, let's say, based on this technology when we compare it with the classic open loop sensors. And on top of this, the Hob will have a much improved DIDT performance or behavior. So usually how we measure the DIDT is we see if there is an overshoot once the DIDT event has happened, and how long it takes for the sensor to settle down, so the settling time after the event. And if we want to compare a classic open loop sensors with that of DIDT, again, we have an improvement of a factor of 10 or 15 on this. So an Hob will improve on or will settle down after DIDT in a matter of let's say maximum 1 microsecond settling time from DIDT events, while on classic open loop sensors you could have long reaction times to 8 to 10 microseconds at least, depending on the amount of DIDT happening.
Thank you, Florian. We can have the next. It's again to Infineon. In which kind of applications is SiC widely used? And how is Infineon enabling to overcome the nowadays design challenges?
So if I want to be pragmatic, I will say that in all the applications that are not cost sensitive, because still the ratio is huge, especially when we compare with the silicon alternative. In the other end, we have to admit that whenever there is a booming in an application, for example, let's speak about the electric vehicle charging or what is around it, new design from scratch are nowadays taking place. So obviously is where it penetrates more. It's also true that renewable and the boosting of the overall renewable, for example, the solar, have made a lot of bring a lot of advantages in this application. We have seen fully SiC-oriented device like in solar boost, for example, but also the combination of both. For example, in a boost having the silicon carbide diode as well the silicon fast IGBT. There are instead other application in which the penetrating factor of the silicon carbide are still not so high. For example, all the application in which the load is an electric machine, for example, in which you basically throw away partially the advantage of the silicon carbide fastness, slowing it down if you want to fulfill the requirement isolation-wise, stress, and MI. In those kind of application, for sure, a key role will be played by the overall system design, so making the drive more integrating, the removing of the cabling around, and also new, probably advanced isolation material in the machine. So it's more at system level, this kind of design and the penetration of the silicon carbide in this application. In the other end, I would like to say that still, even though you slow down the silicon carbide and maybe you partially waste the benefit of the fastness of the switch, it still represents a good opportunity to improve the conduction losses, for example, at light load. So obviously not having the bipolar behavior of the output characteristic. So I would summarize saying that is still there some friction to silicon carbide, especially when the load is the motor. You know, the other application when it's not cost sensitive, then for sure silicon carbide is the way. I'm speaking about those applications because I'm for industrial application responsible, but another kind of application and the overall EV world will be the traction inverter as well as all the auxiliary supply around the electric vehicle. So yeah, I see a bright future for those kind of application and the penetration of the wide bandgap therein.
Thank you, Andrea. We're looking forward to the next. Oh, that's a good question. Why did Microchip decide to offer 3.3 kV devices? I would think there is a market.
Well, that's certainly very true. Though, admittedly, that market is emerging, and perhaps, let's say, not as established as some of the other markets that we're just talking about, like traction inverters for cars and charging stations. But we really do see, and we've had a pretty intense demand from some of our customers to address some of the traditional IGBT 3.3 kV opportunities. For example, traction in trains, those want to operate at the higher voltage classes, and there's been a lot of interest there that we've received. Solid state transformers is another area where we've had some very significant interest. Medical devices as well are looking to operate at some very high voltage ranges, and customers also just looking for that extra protection, as they move into 1200 volt, but of course more into like 1500 volt buses. So we're finding that there is this increasing level of demand. Now, most of the 3.3 kV applications today are still, very early in the design and the development stage with customers, and some are even in the research phase. But we've just found a very strong and consistent level of interest in that next voltage class. And our goal at Microchip is to address the full range of voltage classes from 700 to 3.3 kV, just so that we can also come to our customers with what their needs might be and what their roadmaps might be for the future. So we've done that with our packaging as well. We've got a broad range of discrete devices. We've got modules as well, and continue to develop those through our development centers in France and in Wales and the US and overseas. So we're looking to always offer as broad a range as possible so that we can support as many of our customers' more, we'll call it specialized applications. And that's always been one of our areas of focus. How do we address what the customer's looking for? Not so much, okay, here's what we've got, but what do you need, and how can we solve it? So, that probably opens the door. I can probably see the question brewing, Bodo, about even higher voltage classes, and I know you're probably thinking that as well. So while we don't discuss, future product releases, certainly we are positioning ourselves to be able to address voltage ranges and classes as they continue to grow and emerge.
Yeah, high-speed trains, electrical high-speed trains all around the world are popular, and the plan in general is to reduce air traffic, to bring people into high-speed trains. Electrical, since we overcome the steam age of locomotives, which was really beautiful, and seeing the old steam locomotives in the museums and even on historical rides is something. But the electric high-speed trains are what brings us forward in traffic, reducing CO2 footprint. Okay, gentlemen, I'm looking to my backstage to the next question. Okay, can a customer purchase bare die?
Yep, that one looks like it's also addressed to me as well. Thank you. And the answer to that is yes. We provide our products, as I said, packaged, but also as bare die. We also can provide and do provide wafers to our customers as well. We really do walk into a customer meeting with, a blank sheet of paper, asking what is it that they need. And in some cases, the conversation will start with, we need a certain package, and we may not have it, or they may have their own custom design, in which case they'll want to offer, they'll want to get bare die. Some cases we'll talk to them about bare die, and it'll turn out that they really need a certain package, and we'll sit down and customize a package for them, or modify an existing package. So yes, we do provide everything from the wafers, bare die, discrete packages, modules, and also gate drivers. So we try and really address the full signal chain, from the PWM signal to the output.
Absolutely, Rob. I learned in my life that packaging is not a simple task, and there are not too many companies around the world who can do proper packaging. And I've seen a lot of people who thought that they can do it easily without an expertise in the past, but it's mostly something to fail. The people who have expertise, and I just think, just two good big ones in Germany, for Germany big ones, Semicron and then for Silicon Power merged. They both have great expertise to do so. And I remember there had been smaller companies who thought that they easily could put dye into their applications, and there is a high risk that the soldering and bonding process did not went the way that the reliability will be given, and voiding underneath the dye makes it horrible if they operate then and fail. That's what I learned in the past.
Bodo, that is exactly right. In fact, we've had some meetings with some customers recently as well who were looking for the die, and we left the discussion with working with them to help deliver the full package. And when we talked about some of the issues in integrating die into a package, you can qualify your package, you can qualify your die, but having your die in a package and having that qualified becomes a whole nother matter. I used to be in the connector business years ago, and the single biggest point of failure in any product was always the interconnect. And
absolutely,
I mean, it's anytime you're going from one substrate or to another, and you've got an interconnect, you create points of failure, potential points of failure, and managing.
I fully agree with that. Connectors are the weakest point. And I remember when I was a young man, I had my first Volkswagen Golf called Rabbit in the US,
right,
in the 70s. It had so many functions that started to become crazy until I found out that the connectors for ground had been corroded. So I took all the connectors for grounding out and put new in and screwed them down, not with the fastened 6.3 millimeter connector clips, which were common at that time. I screwed everyone down to the chassis, and I had a fine running car again. That's just history. History, how many years? 50 years ago or so. Gentlemen, I'm looking to my backstage and get the next question. Okay, are there any challenges in simulation for the latest SiC MOSFET JFET devices?
Maybe I can take this one if it's too open.
Go ahead, Andrea.
It always depends which kind of simulation you are referring to, if it's a SPICE simulation or, for example, general system level simulation, PSIM or Plex. For those one, I think there are no kind of issue related to the fact that very well accurate, how can I say, modeling is already provided, especially from Infineon side. We provide both SPICE model as well as Plex model. And I see also competitor doing already that with quite accurate level of simulation and result, especially if we think about system level simulation. What is interesting to see is my, sorry for the advertisement, but my PCIM paper in which we compare exactly, in this case, for IGBT, but it's the same then for silicon carbide. I've done the same process, the validation of the model, the simulation, up to the heat sink, and seeing very well thermal and electrical performance of the simulator. in this case, Plex.
Thank you, Andrea.
Maybe I'll add to that. One sort of area is, most of the suppliers offer pretty reasonable SPICE models and Plex models. But as we look at the silicon carbide devices into newer applications like, solid state breakers and the new places where this very low on resistance affords, many of these models are not well calibrated, let's say for overcurrents and temperature and transient heating, somewhat into what Andrea was saying. So the sort of development of and fidelity of these models in these outside of nominal operation will have to evolve.
Yep, in my case, it was simply for drive application and yeah, Java-wise three-phase conversion, but
to have the full thermal capability in the model is in some case a real nice request, but I remember for SPICE it was always a little bit difficult in the past that it was only set to a certain junction temperature and had not all the changes by operating, which I think is partial now overcome, and you can use models having a good thermal modeling with the models. Okay, what's my backstage telling me? It's a question to Lem. What's the future of HOB and what's the next step?
Excellent
That goes
question.
to Florian.
Yeah, thank you, Bodo. So really, HOB is like a pioneer, let's say, product at LEM. It's the first one doing this kind of bandwidths and going to this kind of uncharted waters. And really, the plan on my strategy, on our roadmap strategy, is to apply this kind of technology / performances and update our current portfolio. So we intend to go to 1 megahertz bandwidth products with our existing other products, while the HOB will continue its pioneer job and will go for higher frequencies. So we are targeting 5 megahertz, maybe why not 10 megahertz bandwidth sensor for the future, for the next step. Of course, there will be redesigns needed because magnetic circuit will have to be redone in order to be able to support this kind of frequencies. So the ferrite that is right now can handle up to 1 megahertz, and we'll have to go and look for some new materials that will be handling 5 to 10 megahertz. But really, the intent is to go higher and higher on frequencies, because we think that this is where the market trend is going, and LEM will be following that market trend.
Florian, thank you.
Yeah.
What's next? Oh, that's a long question. Do you produce or sell 1.2 kilovolt SiC chips? Regarding the packaging, seems the proposed evaluation system uses 62 millimeter modules. Why not SiC Li series? And what would the main applications of 62 millimeter SiC modules compared to competitors' direct cooling DSC modules? How would you expect the electro vehicle market response to SP6 LE? All right. Long question.
I may need you to take that one in stages, or to maybe keep it on the screen for another moment so that I can address it. But and I'll try and be brief on my response with some yeses and nos.
Rob, it's back for you.
So the first question, do we produce and sell 1.2 kV SiC chips? Yes, we do. and we have a quite a broad range of those devices today. So that's a yes or no question. The answer is yes. Regarding the packaging, the proposed, well, it's actually the evaluation system is available, and it uses 62 millimeter modules. Why not SP6LI series? So two answers in there. When we did the development with Mersen a couple of years ago when we started it, the 62 millimeter package was very universally available from Microchip, from Wolfspeed, from Infineon, from a series of other companies. So, excuse me a second. Sorry about that. So we wanted to develop an evaluation tool that would also let customers do comparisons if they chose between different devices from different providers. And as I said, we like to help customers solve their problem, ideally with our products. But really, if a competitor's product is going to be better for a customer, we'll help them, solve what their needs are. Why not the SP6LI series? The SP6LI is now relatively new compared to the 62 millimeter package, and very specific to Microchip. And we developed it because we required, and our customers required, a much lower inductance package. And the SP6LI is currently the lowest inductance module available in the market today. So we are looking very closely at developing an SP6LI version at both 1.2 and 1.7 kV, but we just currently don't have that available. Main applications that we were looking at the time, EV chargers were one. Heavy-duty vehicles was really one of the initial design goals that we're looking to address. It's a 150 kilowatt device, so that would play more in heavier duty vehicles and sort of earth moving equipment. And I forgot what the last question was, but I think we covered most of them. Compared to competitors' direct cooling DSC modules, how would you expect the EV market response to the SP6LI? So the EV market is, again, sort of, generally speaking, could range from a lower-end passenger vehicle, arguably, to, I don't know, maybe even a cargo van or a van that might dart around the city, might consider within the EV market. So currently, the needs there would be more for the higher-end vehicles, higher-end consumer vehicles, and more, we'll call it, light-duty transit vans is where we would see the SP6LI adoption. And again, it would be in a place where someone might look at, comparable low inductance modules from us, from Wolfspeed, perhaps from others. So it fits in that category.
Thank you, Rob. Let's see if we still have something. Okay, is a trench process on the roadmap to Rob?
Yes. So we don't talk about product roadmaps at Microchip. And we certainly don't talk about them in terms of products that we don't offer and don't have, let's say, firmly ready to commit to immediate delivery dates. We tend to be a under promise, over deliver company, so we're a little bit skeptical about going too deep onto roadmaps. But we have been, as you know, have planar based products, and we've seen just tremendous success with those. We continue to improve, increase our voltage classes, continue to improve quality, reduce cost. So that's our currently available, and that's about as far I can go on roadmaps with regard to, let's say, changing of technology platforms.
Thank you, Rob. Thank you, gentlemen. We're coming to an end. No more questions. Here, I want to say so much thank you for this fruitful discussion, and looking forward to see as many as possible of you at PCIM in Nuremberg. I hope after Corona it will be safe event, and I hope that the weird activities in the world of crazy people come very soon to an end, and that peace will be around for all of us, and that we can fight the diseases which can be caused in the world, rather to fight between each other. Thank you, and see you soon in Nuremberg.